Okay, so we're going to get started now. So, hi everyone, and welcome to the Rutgers Geology Museum's Ask a Geologist web series. So, today I'm excited to introduce you all to Christina. And so, Christina Verhagen is a graduate student at Rutgers University in the Department of Earth and Planetary Sciences. And today she will be talking to us about the impact that killed the dinosaurs. So I know I'm really excited, and I'm sure you all are too, to hear about this. So without further ado, Christina, go ahead and you can start.
Hi, everyone. Thank you so much for joining me today. I'm super excited to share some of my research with you um, and just really excited to be a part of everything that Rutgers and the Geology Museum is doing. So thank you so much, everybody. So a little bit about myself. My name is Christina Verhagen. I am from Verona, New Jersey, which is just about an hour north of Rutgers. I've lived in New Jersey my whole life, born and raised. And I've also been a musician my whole life. So I've actually been a classically trained harpist since I was in third grade. Actually, my harp is behind me over there right now, which doesn't get played much these days. But once I got to about high school, I realized that rock and roll and punk rock was really fun. So I kind of ventured into music life that way and joined some bands, did some singing and playing keyboards, and went on tour and did that for a really long time, longer than I ever imagined I would. And music's a lot of fun, but it's also a lot of heartbreak. And bands break up, and you run out of money, and you can't stay on the road. And unfortunately, that time in my life ended. So I decided to go back to school, having a big break from school before. So I had a lot to learn in a short time. I went to Montclair State University, which is up here in North New Jersey, and I graduated in 2017 with my bachelor's degree. And those were my two sidekicks, my weenie dogs, Watson and Whiskey, which kept me company every night I had to study. And then I started at Rutgers right away that summer in 2017. And now I am in the middle of my third and fourth year. So I have 2 years left here at Rutgers. And I work for Dr. Sonia Tiku, who gave a talk a few weeks ago about meteorites. So if you haven't had the chance to listen to her talk, I definitely recommend you check it out. So I obviously love music. I also am an artist. I love painting and wood carving. Here are some of my geology themed wood carvings that I like to do. And I love traveling. And I also, of course, love collecting rocks. So of all the rocks I've been able to collect and all the different minerals, my favorite rock I found is a gastrolith, which is this cool little brown rounded rock. And it doesn't really look like much. But gastroliths are actually stones that dinosaurs would swallow, and they would kind of tumble around in their stomach to help them digest food. And as they tumbled around, they became very smooth. You can see here in this picture, there's a dinosaur skeleton with all these little smooth rocks, all these gastroliths. So I found this rock when I was at my geology field camp in Montana a few summers ago, and I was pretty excited to think that this was in a dinosaur's stomach at one point. So in my research at Rutgers, I study magnetic minerals that are in rocks, which were drilled from meteorite impact craters. So on this picture on the bottom left, you see a meteorite crater. To give you an example of what that looks like, this one is in Arizona. And these are some pictures of rocks that were drilled from the crater. And you can see these rocks have all different minerals, all different pieces of broken rocks in them. And within those rocks and minerals, there's magnetic minerals, which are made from iron. And iron is a naturally magnetic element. So they form minerals like magnetite and hematite. And Chris Lepre actually gave a talk a long time ago about some of that. So you can listen to his talk as well. So these magnetic minerals act like tiny little recorders, and they can remember conditions of the actual impact that happened. So they can remember things like what temperature the impact crater was and how strong the shock wave was that went through those rocks. And then we can measure them to learn more about the impact. So I'm what's known as a paleomagnetist, and paleo just means ancient. So I'm measuring these tiny magnetic minerals to read the recordings and figure out what happened to those rocks in their past. So these minerals can record events that happen during the impact, like the shock wave that goes through the rocks, from the blast of the meteorite hitting the earth, and high temperatures that were in the crater. But they can also remember things that happened after the time of impact. Even millions of years later, they can record how hot the crater was and how temperatures changed through time. And also if those rocks were exposed to waters, and waters within the crater can form new magnetic minerals. So we can learn a lot just by studying the magnetic minerals within these rocks. So meteorite impacts are really interesting to study because they have actually been happening in the solar system since its beginning. So the solar system is over 4 billion years old. And even as recently as 1994, you see in this picture is a comet, which you can see from these, that was broken up into pieces that you see in this strip of white specks that crashed into Jupiter just in 1994. So this is something that has been going on in the solar system for a really, really long time. And when we study meteorite impacts on a crater, they can tell us different things about that planet. Like if the planet had a magnetic field at the time it had an impact. They can also tell us if the planet still has tectonic activity like volcanoes, and if fresh lava has been able to cover up some of those impact craters or not. So we really can learn a lot about planets from far away just by studying the impact craters on them. And the meteorite itself can bring new things to the planet. So it can bring water, it can bring elements like carbon and nitrogen, and the impact itself delivers a lot of heat to the planet. And that heat is an energy source that the planet can then use. So it's also thought that life on Earth actually evolved within an impact crater. And we're actually going to talk about that at the end of the presentation, but so just keep that in your mind for a little bit later, and we'll maybe see how that could be a possibility. So I kind of think about What Killed the Dinosaurs as kind of like a really awesome action murder mystery movie in which we, the scientists, are trying to investigate this murder mystery. So the dinosaurs weren't exactly murdered, but they did go extinct. And when we talk about extinction, this just means when an animal or a plant has died out and you cannot find it living on the earth anywhere anymore. So like any good murder mystery, we need to investigate some questions. So we're going to look into who went extinct exactly, and when did this happen? What caused the extinction? How did the event actually kill the dinosaurs? And what happened after the extinction? So of course, we know the dinosaurs are extinct because we don't see them walking around anymore, right? And we can go to museums and see their awesome skeletons that are preserved. So that's an easy one. But it was actually geologists who first discovered that certain fossils that were of the age of dinosaurs were found in older rocks, but they weren't in younger rocks. So when sedimentary rock layers are deposited, you have a rock layer that's laid down, and then as new rock layers are deposited on top of them through time. So you end up having younger rocks, like today when you walk around on the dirt, and the oldest rocks are below. So when a geologist digs into the earth deep, they're actually going from younger to older. So it's like you're going back in time. And these rocks can be dated using a technique called radiometric dating, where scientists can measure small changes in minerals. And then geologists a long time ago have given specific names to the ages of those rocks. And this is how we get what's known as the geologic timescale. And we can refer to rocks of certain ages that way. So here's a nice example of some sedimentary rock layers. And when geologists were investigating these rock layers, what they found was that in the bottom, older layers, that there were dinosaur-related fossils. And then above those layers, there was no dinosaur-related fossils. And you can see this kind of band in the middle. It was like a very sharp change between having these fossils and not having these fossils. So this clearly needed some investigating. So the rocks were dated, and the lower rocks are part of the geologic time known as the Cretaceous, and the upper layers are known to be part of the Paleogene age. So that layer in between was measured also and was given a date of 66 million years old. So we know that something dramatic happened 66 million years ago. So here is a picture of the whole geologic timescale we're just talking about. So here at the very base, at the beginning, you see, oops, let me go back. You see Earth forms at the very bottom, 4.6 billion years ago, right? And then we go up to this time period here in the middle called the Mesozoic, and that is when the dinosaurs lived. And it's composed of the Triassic, the Jurassic, like Jurassic Park, and the Cretaceous. So dinosaurs lived on the Earth for almost 2 million years, from 250 million years to 66 million years ago. And here we are up at the top, up here by this truck. So they were on the Earth for they were on the Earth for almost 200 million years, and then they disappeared pretty quickly at 66 million years ago. And there's about 65 million years in between dinosaurs and people, just to give you an idea of how long ago these things were happening. So who exactly went extinct 66 million years ago? Well, we know it was actually not just the dinosaurs, but about 75% of all species on Earth, which is pretty crazy. So if you think about that on land, we have all of the dinosaurs that are not related to birds. So all the dinosaurs you've come to know and love, T-Rex, Triceratops, you name it, all those guys gone. And you also had many species of plants on the land. And the sea and in the ocean, ammonites went extinct, which are these cool kind of coiled up creatures here you see in this picture, and belemnoids, which are kind of like similar to a squid-like animal, and large marine reptiles like the mosasaurs. And Kirsten gave a talk a few weeks back about the mosasaurs, which is really cool, so you should check that out too. And there's also 90% of plankton in the ocean went extinct. And Dr. Masha gave a great talk on these types of organisms. But I want you to remember, so these plankton are very small microorganisms that can use the sun just like plants and make their own food and float in the water. And I want you to remember the plants and the plankton, because they're going to end up being pretty star actors in our movie. So keep them in your mind. So what actually caused the extinction? Well, originally, a lot of geologists thought maybe it was due to volcanoes. We know that there was a lot of volcanic activity on the Earth around the time the dinosaurs went extinct. But it turned out that it wasn't exactly at the same time that they went extinct, that 66 million years ago. There was some bursts of volcanic activity before and some right after, but not quite lining up with the extinction event. So scientists then began to measure that layer, that boundary layer in between the two layers containing fossils and not containing fossils. And they measured it to see what elements were present. And what they found was that there was a lot of iridium, which is a metallic element. And this is very interesting because iridium is very rare on the Earth, in the Earth's crust, but it's very abundant in meteorites. So it could be easily explained that this was due to a meteorite impact on the Earth, because you would never expect to find that much iridium without a meteorite. They also were able to measure how much iridium was in that layer, and they came to determine that the size of the meteorite that hit the Earth was about 10 kilometers, which is about like the size of Mount Everest. So it was pretty huge. So an impact that big must have left a giant crater on the Earth, right? So where is it? Well, it turns out there's about 200 impact craters on Earth, just that we can see on the land. And if you see this sea right here over by Mexico, that is an impact crater called Chicxulub. So Chicxulub is a big crater that is with half on land, and you see half of it is buried under the ocean. And it's a really cool type of crater that's known as a peak ring crater. And you can see right here this inner ring, which is the peak ring. Not all impacts have a peak ring. It depends on how big they are. So the peak ring is a really interesting place to get samples from, because we've never actually had samples from a peak ring of a crater before, because this is the first time we discovered one that we could drill into. So you see this red dot here, that's where scientists drilled within the crater and got some great samples, which I'm going to show you. But what they also discovered was that the rocks from the Chicxulub crater are the same age as that boundary layer. They're dated to 66 million years old. So they were able, for the first time, to tie this crater in Chicxulub to the impact that killed the dinosaurs. So how do peak ring craters form? Well, we know that the meteorite was really big, like I said, almost about 6 miles across. So at the time of the explosion, when it hit the Earth's surface, it had the force of 10 billion atomic bombs. And this caused a massive explosion that melted and vaporized the rocks, and it carved out a huge crater that's 180 kilometers across, which is about 112 miles. So here's a cool video just to show you the process of how that would happen. You have the impact hit, and it instantly vaporizes and melts the rock, and then the Earth's rocks begin to rise up in the center in response to the force, and they can't carry their own weight anymore, so then they collapse over onto themselves, and this forms the peak ring here. And that's where the scientists drilled into. Right there is the peak ring. And again, that peak ring formed from these rocks in the middle that lifted up and then spilled over on their sides. So it's a pretty cool example. I'll show you one more time. There you go. And you can see here the Earth's crust is being spit out all the way and deposited all over the land. And other pieces of rock are being spit out into the atmosphere as they're melted and vaporized as well. So pretty violent explosion. So when they drilled into the peak ring of the crater, they drilled straight down at one spot. So at the bottom of the drilling, they have granite rocks. And these are rocks that are similar to like something you'd find on your countertop. They're very hard, very old rocks. And then they're covered with impact melt rocks and breccias. So we're going to go through the 3 of them. And remember, older is at the bottom. So the granites are the oldest rocks of the crater. And these granites were fractured and broken up when the meteorite hit and the shock wave went through the rocks. So it fractured them as it went through. Then, just about 10 minutes after the impact happened, melted rock from the explosion filled in the crater. And you can see by these are pictures of the actual rocks. So here, there it's black and green impact melt, and you can see that they were just completely melted. They don't have nice mineral structures like you see in the granites below. So about 15 minutes after the crater formed, you had a tsunami wave come and fill the crater. So if you remember, the impact happened off the coast of Mexico in the ocean, and it was very shallow ocean there. So the impact caused a tsunami wave, which came rushing back into the crater, and it filled the crater with seawater and broken rocks. And these broken rocks formed what's known as a breccia. And breccia just means a rock that's made from other rocks. So you can see both of these are breccias, and you can see that they're made of all different size rocks, some small ones, some big ones, and they're all cemented together. So they're pretty cool rocks to look at. So these are all the rocks that I study at Rutgers, and all of them contain magnetic minerals. So it's really a lot of unwinding and untangling of storytelling that we have to figure out within these magnetic minerals. So how exactly did the impact make the dinosaurs go extinct? Well, this is the action part of the movie. At the time of impact, like I said, there was vaporized and melted rock that was flung into the Earth's atmosphere. And as these pieces of rocks cooled, they began to descend back onto the Earth's surface. So you had fireballs, and you also had earthquakes from the impact and tsunami waves. And all of this happened immediately. You then had burning fires that happened on all the continents of the Earth. And all that burning caused soot and ash to build up in the Earth's atmosphere. And this would have caused cooling as it blocked the sun's light. And it also would have caused acid rain as it rained and precipitated a lot of those noxious chemicals out of the atmosphere. Now that was going on for months. So it's a pretty hellish scene to think about, burning fires and acid rain going on for months at a time. And all of that would have killed and damaged plants and animals around the world. Now, remember we talked about the impact happening in the ocean. So the rocks that were in the shallow water of the ocean near Mexico are called gypsum, and they actually contain an element called sulfur. Now, sulfur is an interesting element in that when it's released from a rock, it can build up in the atmosphere for a long time. And all that sulfur in the atmosphere would have blocked the sun's light. And when you block the sun's light, you then, all the plants that are using the sun for food as they perform photosynthesis, all of them would not be able to make food anymore. So they would die and the earth would become a lot cooler. So you had no sunlight for years because of the sulfur. So if you remember our star players, the plants on land and all the plankton in the sea, well, they began to go extinct and they began to die because they could no longer make photosynthesis and no longer be able to live. So basically you had the collapse of the food chain at the time. So any animal who ate plants or ate plankton in the sea began to die off because they didn't have a food source. And then all the other animals, the bigger dinosaurs and the bigger animals that ate those other animals, they began to die off. And it just kept going until all these species went extinct. So the only things that were able to really survive was small animals who could hide and burrow and could also eat very small things like insects or decaying plants and animals, since there was so many dead animals around. They were the only ones that were really able to survive. So in a nutshell, the dinosaurs went extinct because the meteorite impact caused their food sources to disappear. Very sad. And that's the end. Okay, I'm just kidding. It's not the end. But every good movie has a sequel. So I thought we would now have part 2, which is who survived the dinosaurs. And in this one, we're going to talk about any animals that survived as well as microorganisms. And us scientists are still doing the investigating. So life after the impact, who survived? Well, on land, we had birds, which are actually related to the dinosaurs. They were able to survive. And we have crocodiles, reptiles like snakes and lizards, turtles, amphibians, and mammals. Now, mammals at the time of the dinosaurs were very small because if they were any bigger, the dinosaurs would have eaten them. So they stayed pretty small and they didn't evolve to become much bigger, and they were able to hide and still live with the dinosaurs at the time. But they were small, so they made it through and they were alive. So it's pretty smart of those guys to stay small. In the ocean, we have fish, sharks, corals. Some plankton species were able to survive, thankfully. You have what's known as bivalves, which are like clams and mussels. Colloids, which are like octopus and squid. And these really cool guys called the nautiloids. So there was also life after the impact in the crater's rocks. Now I know that sounds weird, but there can be life in the rocks. So I'm going to explain it to you. Okay, so when you look at a rock, it looks really hard, right? But there actually can be pore spaces in the rocks. And if you were to look at a rock up close, there you see all the different minerals that are kind of touching each other and around, but there's actually spaces in between some of those rocks. And if the rock has any fractures or cracks in it, that's even more space. So all of that is pore space, and water can actually move through those pore spaces of the rocks, especially heated water. So a hydrothermal system is a system where you have hot water, which is what hydrothermal means. So you have hot water that's moving through pore spaces and sneaking its way around any space it can find. And in these tiny spaces in the water, microorganisms can make their home. And in heated water, you have a lot of dissolved nutrients, which the microorganisms can use for energy and food. So if you've ever heard of a black smoker, this is what you find on the seafloor. And these are hydrothermal systems on the ocean floor where you have very heated water that's moving through the rocks of the ocean crust. And we know that microorganisms live in that very unhospitable place. It's very, very hot, but these organisms can still live there. And at Yellowstone, if you've ever been or seen pictures like this, you have these beautiful hydrothermal deposits where, again, you have hot water that's been moving through these rocks and microorganisms that are making their homes in there. And that's exactly what we see in the Chicxulub rocks from the impact crater. So here is one of our breccias, again, the rock that's made of all the little rocks cemented together. And you can see this red kind of wave in the rock. Well, that red is a hydrothermal mineral called sodium daciardite. And it forms from the water, it kind of precipitates and it forms in the spaces of the rocks. So we know that the water moved through the rocks in that pattern and deposited this mineral. Now, I'm studying all these rocks and the magnetic minerals to learn specifically about Chicxulub hydrothermal system. So what we've discovered so far is that temperatures in those waters in the rocks were originally 400 degrees Celsius, which is 750 degrees Fahrenheit. Now that's way too hot for any organism to live. So it started really hot and nothing was alive in the crater after it formed. But then through time, the crater began to slowly, very slowly cool. And as it did, there are heat-loving organisms, which we were talking about from Yellowstone and the black smokers, and they're actually able to live in water that's about 250 degrees Fahrenheit. And they really like the heat. They use it as energy, and they love all those dissolved nutrients. So what we found is that those waters were a nice temperature for these organisms to live for at least 150,000 years. Now, Chicxulub is a big crater, but there's even bigger craters in the solar system that are much bigger. So we can imagine that those impact craters could have had hydrothermal systems that lasted much, much longer than 150,000 years. And when you have these wonderful environments for organisms to live in, where you have heat and energy, you can imagine that life can really set up there and make that place its home. And through time, it can evolve and change. And this is why we think that life may have originated on Earth in an impact crater, because it would have been a very nice place for life to be. And at the time, you would have had a lot of impacts happening. So being on land and being on the Earth, it would have been very dangerous for life to start there. So this is kind of like almost like a little nest where life can grow. And again, this just tells us that a hydrothermal system is a really good place for life to evolve. And here's just some more pictures of my samples that I'm working on. And you can see these are all the breccias. And you can imagine with all these different pieces of rocks in here that there's a lot of space for that water to kind of move around. Now, impact craters, like I said, have been happening in the solar system from its beginning, but they're also all over the place. We see impact craters on our moon. We see them on planets like Mars and Mercury, and even other planets' moons, like Enceladus is one of Saturn's moons that we see impact craters on. And asteroids themselves can have impact craters. So there's plenty of impact craters to look for life. And we now know that impact craters are a really good place that we should be looking for life in the solar system. And it's cool that we have them on Earth and we can use these rocks to get an idea of what's going on in the solar system around us, since we can't actually go get rocks from all these places. So just one more thought before we end. If you think about it, if the impact occurred anywhere else on Earth, if it didn't hit the rocks in Mexico that had sulfur in them, well, then the dinosaurs might not have gone extinct at all. And if the dinosaurs didn't go extinct, then the mammals wouldn't have been able to grow bigger and evolve and change and eventually lead to the evolution of us. So if this impact didn't happen at that time, at that place, we might not be here today. So we have to be pretty thankful for that meteorite, if you ask me. And with that, I'm happy to hear any questions. Thank you guys so much for listening. Yeah.
So you can stop sharing your screen now, Christina.
Okay. Okay. Should I go ahead and look at questions?
So you can start answering the questions now.
Okay. Okay. You guys have some great questions. Okay. So first question from Mary in Scotch Plains. When did the seawater cover up part of the impact crater? Well, we know that the impact crater formed within minutes, and it was actually about 15 minutes later that the water returned back into the crater. So it was actually really very quickly. Did the ground rebound after the impact? And if so, how quickly? That's a great question. It did rebound. So if you remember from that video I showed you, the Earth's crust originally was flat. And then as soon as the meteorite hit the Earth's crust, the Earth responded to the force of that impact and began to rose up and formed the central peak of the crater. And then eventually that spilled over to form the peak ring. And again, that happened within minutes. How long would dust stay in the atmosphere, and how high would the dust stay aloft? So dust and soot from the fires would have accumulated in the Earth's atmosphere, but they could actually precipitate out through rain fairly quickly. But sulfur is really the problem here. Sulfur, once it reaches the upper atmosphere of the Earth, it can stay there for years. And that's really what made everything so detrimental to the dinosaurs, is that you had so much sulfur in the atmosphere and it blocked the sun's light for years. How did the impact disrupt the sea? Well, again, we talked about the tsunami wave. So you initially had that really giant tsunami wave that formed and then came rushing back into the crater. And then you would have had a lot of waves back and forth within the crater. And that's what's depositing those breccia rocks that we saw. How did they find minerals caused by the impact? Did they find any minerals caused by the impact? Yes, they found, well, the iridium, like we had talked about. And also there are what's known as tektites, which are little glass that's formed as that melted rock goes into the Earth's atmosphere and then falls back down. And they found those all around the world, especially in the Caribbean, and they were able to date those rocks to the time of the impact as well. And there's also something called shocked quartz, which are quartz minerals that have been altered by the shock wave, and it changes kind of the structure of that mineral. And they found those around the impact as well. Are there any rare elements besides iridium that are associated with meteorites? Definitely. You can see nickel is abundant in meteorites, and also chromium, which is another metallic element. And chromium, they actually used chromium to determine that the type of impact that hit Chicxulub was a carbonaceous chondrite. So that's another really important one. Was the meteorite impact strong enough to send meteors out into space? This is actually cool. I didn't really, you get so focused on Earth, you forget about the rest of space. But it actually, as far as I know, we can't go to planets and the moon and just pick stuff up and figure out if it was from Earth originally, but some scientists have done computer models, and they have determined that debris from the impact, or rocks and things from the impact, would have definitely been ejected into the solar system, even maybe as far out as Saturn. What new tool or test would you like to invent for your research? That's a good one. We talked about the black smokers and the seafloor. Well, I think it'd be really cool to investigate the hydrothermal systems on the seafloor, because those would have been around from the very early Earth also, and determine what's a better environment for Earth to evolve. Would it have been in a seafloor hydrothermal system, or would it have been in an impact crater hydrothermal system? But sometimes the hydrothermal systems on the seafloor are a little trickier to measure and investigate, because the magnetic minerals kind of can get scrambled as time goes on, and they're harder to read. So I would really like to come up with a way of measuring them and kind of being able to unravel the mystery of the seafloor rocks and be able to see which system is better for life. Since somebody was looking for oil when the impact crater was mapped, did they find oil? So we didn't talk about that, but originally the Mexican oil companies were drilling into the crater because they saw this circular structure and they thought that there could be oil there. So they were the first ones to discover the impact crater itself, and they did do some drillings first. They didn't find any oil, but they did, of course, find the impact crater, which is kind of cooler. But the rocks that the meteorite hit may have contained oil, as nearby rocks do. But at the time of impact, the impact would have completely obliterated and vaporized those rocks. So which also could have been a source of carbon dioxide, which is another greenhouse gas which builds up in the Earth's atmosphere, could have been released because of that. Do you find evidence of impact dust or debris on other parts of the Earth, like ice cores or sandstone layers? Well, we talked about the tektites and how you find evidence of that. It's known as the Cretaceous Paleogene boundary layer all around the world. They do see evidence of that. As far as ice cores, during the time of the impact, the Earth didn't have any ice on it. There was no Antarctica, no Greenland ice caps, so they wouldn't be able to record anything in the ice. The ice sheets in Antarctica didn't form until about 30 million years after the time of the impact. When and why did scientists change the name KT to KPG? So originally it was called the Cretaceous, the bottom rocks, Tertiary extinction event. And then in about 2008, they're working on redefining the geologic timescale that we saw and defining those time periods based on fossils and different things. So they made it an even better system, and they kept Cretaceous, but they changed Tertiary to Paleogene and Neogene. So the Paleogene is from about 66 million years ago when the dinosaurs died to about 30 million years ago. And then after that is the Neogene, which is 30 million years ago to today. Leah would like to know, we learned about breccia in the session on the moon. Are there any similarities between the breccia on the moon and the Chicxulub one? That's a great question. Yeah, breccias are, really interesting rocks because they are like an action shot. They form by rocks in the sense of an impact crater. You have rocks that are falling in. So they would have formed in a similar way. If there's water, like on Chicxulub, you have the rocks falling in the water. So like if you think you have the ocean and you dumped a bunch of rocks in, they're kind of slowly falling to the bottom. Where on the moon, if you don't have water, you would just have rocks kind of tumbling in without water. So there will be differences in how they were deposited, but the rock and the minerals that are in there, but the rock type themselves will look very, very similar. Aren't the Deccan Traps in India dated to pretty close to the time of impact? Yeah, so the Deccan Traps are the name of a really, really big volcanic volcanic spill of lava that happened in India. And it's really, really big. So when a volcano emits lava, it can release carbon dioxide and methane and all these different gases that build up in the atmosphere and can kind of do the same thing, block the sun's light, cause cooling. So for a long time, that was what we thought was responsible for the dinosaurs' death. But like I said, they have dated, when they date these kind of volcanic pulses, so the volcanoes were spewing out lava, and not all at once, but over time, like a little bit here, a little bit there. And there are pulses of that lava and volcanic activity before the dinosaurs went extinct and after. So most likely they kind of teamed up together. So you already had an environment where bad gases were building up in the atmosphere and already kind of starting to affect plants and photosynthesis processes. And then the impact was just like the last blow. It was like the last shot of the gun that just kind of ended everything. So they probably worked together, although the impact occurred exactly at 66 million years ago. Ria's mom would like to know, have asteroids been the cause of any other mass extinctions? There's a lot of people think possibly that they could have been responsible for different for different extinctions, but there's never been any other evidence other than Chicxulub. So we've never been able to find an impact crater that we can exactly tie to the extinction like we can in Chicxulub. And this could just be because Earth is a very dynamic planet. We have volcanoes. So when you have a volcano, it can cover up impact craters. We have an atmosphere, we have rain, all of that can erode an impact crater and make it kind of disappear. And we also have subduction of the Earth's crust in the ocean. So if you've ever seen a subduction center where you have the Earth's crust slides underneath it itself, the tectonic plates move and one goes below the other. And any impact craters that were on that slab that is now subducting, well, that's lost forever. We'll never know. So it's hard on Earth. We don't have a really good, even though we have so many impact craters, there's so many that we have lost due to all these processes. The ocean must have been an acidic place after the extinction. How did sharks survive that? That's a cool question. I don't know the answer to it because I don't know that much about sharks, although I think they're really cool. But I would imagine that maybe where sharks were able to live, they were very large. If they were able to stay deeper, that they would have been able to kind of avoid any of that ocean acidity that's happening in the surface layers. So maybe that could be one way, but I'll definitely be looking that one up. Are there hydrothermal vents in the crater? So like we said, the crater was filled in by water really quickly after the impact event. So that means that you have the breccias, and then you start to have the return of sediments, sedimentary rocks within the crater, and that's formed of different minerals like calcite and things like that, and sands and limestone is forming. So there is evidence of some hydrothermal vents, which basically is you have hot water moving through the pores of the rocks in the breccias, and it's moving up. And when it gets to the top of the breccias where the sediments are, it comes through. And there is some evidence of venting, so where the hydrothermal waters are coming out into the sediments and onto the seafloor within the crater after the time of impact. And any organisms that were living at the seafloor would have been able to use that heat and use that energy, as well as any nutrients, different elements that were dissolved in the waters as well. What would a potential source of heat be for the vents near the crater? So the impact crater was able to stay hot so long. Remember, we said it was like 150,000 years. So it was able to stay hot that long for two reasons. Remember, when the crater formed, it filled in first with impact melt and then the breccias. So the impact melt is really, really thick. I think in some places it's up to 3 kilometers thick melted rock. And that would have taken a really long time to cool. So as it's cooling, it's giving off heat, and that's one source. But if you remember, when the crater formed, after the meteorite hit the Earth, the central peak of rock came, right? It rose up and then it spilled over and forms a peak ring. So the central rocks that were still left in the middle, they were originally buried very deep in the Earth's crust. And as you go deep in the Earth's crust, temperatures get higher. So they were hot to begin with compared to the surface of the Earth. So as they rose up, they brought that heat with them. And now those rocks are not deep, but they're at the surface. So while they're sitting there at the surface, they're giving off heat as well. So you have two sources of heat for a very long time. And that's what would have allowed the water to become hot and move through the rocks for so long. What type of crater is the Chicxulub, and what are some other kinds we have on Earth? So as we mentioned, the Chicxulub crater is a peak ring crater, and we now know how the peak ring forms. But you also can have you basically have very simple craters to very complex craters. And a simple crater is just like a bowl, like if you scooped ice cream out of the Earth, it's just a scoop out. And then as the crater gets bigger, as the impact event is bigger, you will be left with a more complicated crater. So you have the peak ring, and then you have even more complex craters, which have more than just the peak ring. They have many inner rings. And this depends on how big the impact meteorite actually was. And it also depends on a planet's gravity as well. So there's kind of different ranges for meteorite impact craters on Earth or the moon also. Okay, Mark would like to know how anoxic and acidic did the oceans get following the impact? Like I said, the surface oceans would have been pretty acidic due to all the carbon dioxide buildup within the atmosphere originally. Um, oh, and but within the impact crater itself, you have it's not really closed off. So there's other impact craters. If it formed and was closed off from the ocean, so it formed, it filled with water, and then that was it, it would become very anoxic, which means it doesn't have a lot of oxygen in the water. But when Chicxulub formed, there was a portion of the crater that was left open, so fresh ocean water could flow into the crater. And as the fresh ocean water flowed in, it brought oxygen. So within the crater, conditions never really got very anoxic. They do. We have also found, scientists have found that there was pretty much life returned to the sea and to the sea in the crater very, very quickly. So within right away you still have creatures that are living in the microorganisms that are living within the ocean in the crater itself. And a lot of these are called survivor species because they can survive something as traumatic as that. Did anyone find impact diamonds? So not that I know of, but I know an impact diamond, what Mark is talking about is basically diamonds are formed from carbon under high pressure. And that's how you get a diamond. So technically, a meteorite impact has a lot of pressure, and if you have carbon, you could technically make diamonds. I imagine this would be a cool thing to go mining for. I don't know if anybody's found them at Chicxulub as far as I've ever come across reading, but it's cool to think about. Rob would like to know, how often has an impact of similar size hit the Earth since it was formed? Should we be worried we might get another one anytime soon? So Chicxulub, as we said, the meteorite that formed the crater was about 10 kilometers across. And meteorite impacts with a meteorite that big only happen every 100 million years or so. So we're actually okay as far as you think about it, since that was only 66 million years ago. We still have some time, hopefully. Other impacts that are smaller happen more frequently. So you have like dust-sized meteorites, like dust-sized particles that are hitting the Earth every day, all day long, and you never know. They burn up in the Earth's atmosphere. But as far as something big that would actually do damage to the Earth, we don't really have to worry about that. I think anything about a meter in size, which is significantly smaller, happens every year. And anything that's like 100 meters can happen every 10,000 years. But again, these things aren't going to cause huge catastrophes like the KPG extinction event. And NASA is doing a really good job at tracking all nearby asteroids and meteorites. So hopefully, if there was one to suddenly come upon us, they would have some master plan. Why did the Mexican oil company think there would be oil in a circular rock formation? Oil, okay, so when you have rocks that contain oil, they are sedimentary rocks, which have lots of pore space, like we talked about. And that's where the oil is in those pore spaces. Then a lot of times on top of that rock, you'll have a different layer of rock that isn't very good that doesn't have a lot of pore space in it. So you have a very porous rock and another rock that doesn't have as many pores, and it traps the oil in that bottom rock. So what these geologists will do is drill into that first layer in order to get to the layer with all the oil and then be able to extract the oil. So the shape of the crater, basically having those concentric circles, they thought it would be a good place where oil could get trapped underneath those rocks. And they knew that there was oil nearby and similar rock types. So maybe because these weird shapes were, they were seeing these weird shapes by looking at maps from above, and imagining that it would be a good place for the oil to get trapped. Why did you decide to pursue geology? I actually just have loved rocks genuinely since I was a little tiny girl. I had rocks in my pockets as far as I can ever remember. My mom said she used to do my laundry and just hear rocks tumbling. And to this day, I still have rocks in my pockets. So I don't know, I just thought rocks were super cool. And when I decided to go back to school after music, I started thinking about, what's a good job? Could I make money doing this? And then I just thought about what I loved, and I thought about rocks. And I didn't imagine that people went to school for rocks because I never knew anybody who did. So it seemed kind of strange that do they even have degrees in rocks? But turns out it's quite popular, and I was really excited to find that out. And honestly, I adore doing it, and I love learning more every day. And it's great if you love something to be able to read about it every day. So I'm super happy that I decided to go back to school. What is the most exciting place that you have ever traveled to for your research? That's a good question. I guess when I was in Montana for field camp, that was really, really cool because we always talk about these layers. We talk about all the layers of rocks and you see pictures, but when we're from New Jersey, so you don't get to see that many rocks. We have a lot of buildings and highways and stuff. So when you are finally out in a free open space and you see all the layers, like as far as your eye can see, it's just absolutely amazing. I never wanted to come home. It wasn't for research, but I did go to New Zealand 2 years ago for a vacation, and that was that was probably the coolest place I've ever been. There's like wet rainforests that are cold, and just you feel like you're in Jurassic Park, like you expect to see a dinosaur walking up to you, and there's a lot of really cool geology there. So that was probably the coolest place I've ever been to so far. Hopefully I'm going to be going to the Atacama Desert in Chile either this year or next, and we'll be looking for meteorites in the desert. So that might take the cake. That might be the top one when I get to do that. Okay, let me see if there's any other questions. Okay, let's see. There's one more. How are the small creatures able to survive just by hiding? By Max Lee. They actually were, by hiding, they were able to hide from a lot of those fires and different things that were happening originally in the very beginning. So they would have been protected from all of that. But they also would have been able to hide from any larger animals that would want to eat them. Because remember, a lot of food sources were disappearing. So the smaller you were, if you could hide, you're going to be safer. For sure. And they also, because they were small, they're able to eat a lot of different things. So they didn't rely on having as much food. They could eat, little tiny insects and decaying pieces of plants, and that's how they were able to survive. And I think that is it.
Okay, Christina, thank you so much. And that was really interesting. And so for everyone else, thank you for joining us today. And don't forget to tune in on Thursday, June 25th. We will have Christina Hayek. She's a naturalist educator at the Westchester County Department of Parks, Recreation, and Conservation. And she will be speaking to us about turtles. So that will be on Thursday, June 25th at 11 a.m. And thanks once again, Christina, and enjoy the rest of your day.
Thank you.